think I have something here. Find a difference. No, I don't have it here. So let's do it from the beginning. So what we are going to do is to do some numerics now for the simplest equation. Because I need to have this in your way of thinking. So imagine you want to solve just du dt plus or equal, just equal here, du dx. Huh? Not big deal, you know the solution of that is u of tx, if you give some initial data t equal to 0, is just u0 of t plus x. Right, because if you take a derivative with respect to t, you get a u prime of the same argument, and if you take with respect to x, you get a u prime with respect to this argument. So this is a wave traveling to speed 1 in this direction. That's all what it is. And we are going to use boundary condition, periodic boundary condition. So you take that u of tx is going to be the same of u tx plus some distance L. So we are really solving in the cylinder, in a cylinder like this. And here we are going to use what is called method of lines. Okay, that consists in say, okay, since I have this equation, I will discretize in time, in space, sorry, and leave the discretization, leave the time continuous. Huh? So I'm going to just take a discretization of space. So in this thing here of length L, I will discretize with points, equally spaced points. You can do with other, with non-equally spaced point, and actually sometimes it's okay. This point is not going to be here, because this point is the same as this, because periodic boundary condition. So this point is going to be 1, 2, 3, 4, 5. But there are, how many elements there? 1, 2, 3, 4, 5. So delta x will be the length I have divided by the number of points. Yeah. So we are going not to solve here, but to solve a system which has the time here as continuous, but only this point. So instead of solving this equation, we are going to solve an equation for a variable bi, a vector, I equals to 1 to n. And we are going to discretize this derivative. So, and for that we can use, so this is bi to dt is equals to, I have to put a finite difference resembling the derivative approximating. So I will take bi plus 1 minus bi minus 1 over 2 delta x. So to compute around here, I'm going to use the values here. To compute along this line, I'm going to use this value and this value. And of course, when I'm here, I will use this value and this value, right? Because I'm just here, so this is the one in the left. And when I'm here, I'm going to use this value and this value, okay? So these two values are for computing here, and these two values for computing here. And to compute here, I have to use this value and the other value on the other side, which is this one. So one have to be careful that when we say that the bn is equals to bn plus 1 is equal to b1, okay? 2, sorry. And so, and b minus 1 is bn. So I have to be careful with that. So we are going to use this method first. So what is this? So we have the derivative here of a vector b1 to bn, and here what we have is a matrix applied to this vector. Right. This metric is, okay, let me put the 1 over dx here, 2, so I don't have to repeat. And this metric, for the same first element, it has 0, b2, which is I equal to 2, sorry, a 1 here, I'm going to put a 1 just. A 1, this is the one that goes in front of this. And I have to consider this one, right? And this one is the minus 1 is bn. So it's the last point here with a minus sign. So in this metric, is the last point is a minus 1 here. So these are zeros. The second one has a 1 here because it's this one, a 0 and a 1, a minus 1 here, and then zeros, and so on. And the last one, which is this point here, has a point immediately before with a minus 1. And I have to have this point, right? Here, this point. So I have a 1 here, and then 0. No, this is, I'm doing something wrong. Hold on. For this I need this is a plus. No, this I'm in the end. This is wrong. This should be minus here, and this here. This should be 0 here. So I'm here. There is a minus 1 here, and there is a 1 here. So there is a 1 here and then 6. Okay. So this is symmetric. And here in the previous line there is a 0 here in the diagonal, minus 1 here. And 1 here. This is also wrong. This should be, these ones are positive. This is positive. These are negative. And this should be this is yeah. I think it's okay. Yeah, that is. So this, as Pablo said, is antisymmetric. Huh? This A here, this A matrix is antisymmetric. And here you have B again, right? So this is a system. So we are approximating the continuous equation here with this equation, which is, so we are approximating the space derivative with a center scheme. Why center scheme? Here I could have used, for instance, Bi minus Bi minus 1 divided by delta x, or I could use Bi plus 1 minus Bi over delta x to, or these are possible, but they are not good. So, and these are order delta x, so the error from the comparing this with a function evaluated at this point, a smooth function, is the error you make goes to 0 like delta x. When you do this, it goes to 0 like delta x squared. But also, it has better properties. And the main property it has is that this in here is antisymmetric. Okay? So this matrix is antisymmetric. So we have this system now. dt dv dt is equals to 1 over 2 delta x times the matrix A times B. And we know the solution of that, right? The solution of that is V of t equals to e to the 1 over 2 delta x a t times b at t equals to 0. Okay, so you give this value and you can solve this. Well, we study what is the exponential of a matrix, right? To look at the exponential of a metric, you have to look at the metric, get the Jordan form, write it in blocks of Jordan forms, and then every Jordan form block you can compute it. Right? But notice, this metric is antisymmetric. That means that I times A is self-adjoint. Okay? Because with the I, you get basically you get a symmetric matrix, huh? Because when you take the complex conjugate, the I becomes minus I, and so something that was antisymmetric now is self-adjoint, is harmonic. So B I A U is the same as I A complex conjugate apply to B U. Because when you move it here, you change the side of the indices, but they complex conjugate, and that give you from minus I, you give you I. From I give you from minus I, because the change in the antisymmetry of this, and the complex conjugate give you I again. So since this is Hermitian, it has real eigenvalues. It's diagonalizable and have real eigenvalues. So this matrix has imaginary eigenvalues, the A. So this here is e to the 1 over 2 delta x lambda I t, and you have to here you have a sum of the eigenvectors with coefficients, right? So you have here B let's call it K here, and these are big elements BKs and the base elements. So here I'm using the AK is equal to lambda K AK. We have a complete set of eigenvectors, eigenvalues, and so for each one of them, if you write this in this linear combination, you get that the solution is this here. And if these are, I say these are imaginary, so I will write this as I times real things. So that I have real thing here and imaginary. So these are all okay, they just go around. And this is the way you compute the solution. This is the exact solution of this system, right? So if you take delta k equal to 0, delta x equal to 0, this is going to go to infinity, but you take many of these things and you approach, this is like Fourier series, basically. It's a Fourier series decomposition, no more than that. This is a Fourier series decomposition using as eigenvectors this thing here, the eigenvector of this. And we can compute this. This is not difficult. I'll show you what this E sub k are. But maybe today or maybe tomorrow. Okay, but now that we know this intermediate step, we know how to solve this, we can say, okay, this what we have here is a set of ordinary differential equations, right? A very easy one, just the one we study, or if we come here, in the base of this is a very easy system. In fact, we have solved it. But then we have, okay, this is a system of ODEs, so I can get the numerical of these things with some of this one step method, huh? Say Runge-Kutta-4 or whatever. So what we do is to put this system, solve this system, using some one step method. Okay? And when we get to there, we say, okay, if we write this in the basis, right, we have many systems which are like BK, so in the base, so I write the equation in the base. So we have this thing equals to I lambda k over 2 delta x bk. So we have the system we studied already, where this lambda now is all this in here. So lambda from this system is I lambda k over 2 delta x. So when we multiply by delta t and get the mu of the system, remember that we use mu was lambda times delta t. This thing here is I lambda k over 2, and then you have delta t over delta x. So in the complex plane, let me change colors. In the complex plane of mu, this is real, this is imaginary. These points are all here. So if we try to solve this with Euler's, we are going to be in trouble because Euler is only stable here. These are right. These are stable. The solutions are all bounded by the value of bk, the initial value of bk. So this is going to be here, so it's going to be unstable, and you, even if you take delta t going to 0, which is moving along this line, the convergence is very bad. And remember, this number here, you want to make it very small, so this is very good, very large, so you need to take delta t also very small to be finite. But here you need to send it to 0, so delta t should go faster to 0 than delta x. Now, if you take a method like Runge-Kutta-4, Runge-Kutta-4 has stability region which is sort of like this. Well, it's actually bigger, it's like that, something like this. So Euler is this, and this is Runge-Kutta 4. So if you take a method like that, all the axis is in the stability region for delta t small enough, and so you can solve it, okay? So we will be solving this problem, this exact problem. And what you should get is, as we say, some wave moving to the left. So this is a point why we need to consider, study the stability region of the methods and use a method that contains, for these hyperbolic equations, the real imaginary axis. So let's stop now. The next hour we are going to discuss finite difference, which is the thing we need to know better now. We have Runge-Kuttas, now we have to know all about the mathematics, the approximation for these things. Huh? That's what we are going to do next hour. So let's take, start at 12:10. Are there questions? No questions on the other side? Nothing? Okay. We stop now for a while. Okay, we continue now. Are there questions? If you ask question, I know what are you understanding or what you are not understanding, whether I'm going too fast or too slow. So please make questions, either via chat or just open the microphone and make questions. Okay, now we are going to move to I think it's this one. Okay, I have to open it first. So now we start studying finite difference, okay? So these are approximations to derivatives. So you take a finite grid, and you take discrete points. So the delta x is the difference, is the distance between two consecutive points, and we are going to take equally spaced points. So delta x is fixed for all. So we have 1, 2, 3. And here this point is the point x0. Oh, here I'm using another notation, so this point here is the point 0. Sorry. This point here is 0. Okay, so now the number of points is delta x is the x initial, x final minus x initial divided by n minus 1, because I'm starting in 0. So we have points x0 plus I dx. These are the points starting xi, starting with I equal to 0. So 2 n minus 1. And we close, for the case of periodic problems, we take 1 point less and close. So as I mentioned before, we could take these operators, the d plus and d minus. These are the operators sorry, I try to here. These are the operators where you take the plus has the derivative, the point to compute the derivative here, you use these 2 points, I and I plus 1. The minus uses this point and this point. So it's towards the right and towards the left, right? For a continuous differentiable function, both tend to the same value when delta x goes to 0. But in finite difference, they are different, right? Clearly. So we can see the error that we make in computing this instead of this, of the derivative. So we can do a series, Taylor series, to get this value from this. And so this will be plus minus the derivative at the xi times delta x, the plus for going to the right, the minus for going to the left. Then we have a term which is, we have the same sign for both, which is the delta x squared. And again, right, for even powers you have a minus or plus for odd powers, and for even powers you don't have the difference. And so now you can look at this difference is then, that's the definition, and is the derivative at the point plus an error that goes like plus minus the second derivative times delta x over 2. So the error here is it goes to 0 like delta x. So if you take the center difference, that was the one that we took before, that is, you take the plus and the minus, divide by 2, and you notice that the error here has a sign. So it's plus for the plus derivative and minus for the minus. So if you take the average, you cancel this term, and so you get that you get the derivative plus a term which is the third derivative of u times the delta x squared over 6. So for things that are 3 times differentiable, this approximation is much better. Notice that since this error is the third derivative, so if I take a polynomial, say u equals to a plus bx squared, then since the error, no, x only, so, no, it's okay, but right, bx plus cx squared, since the third derivative of that is 0, this formula is exact for polynomial up to second order. So one way of finding the coefficients when one is trying to get a good approximation is to use polynomials. So you center the polynomial at the point I and use these polynomials. So that's a practical way of computing the coefficients of the finite differences. So if you want higher accuracy, for instance, you say, okay, I want to get a fourth order operator. You use you write the operator you want to compute this way. Notice that here we are making it symmetric on the left and on the right. That's because if you make it symmetric, it will be 0 for, well, anti-symmetric. It will be 0 for all polynomials which are of even degree, right? Of odd degree. So a quadratic polynomial will give me this 0 because centered at I equal to 1, at I, right? So if I have a polynomial here, this is the point I, and I have several points here, the derivative will give me here, will give 0, identical, right? So I can use these to cancel all the even polynomials and only have to look at the odd polynomials. So that's why we take it to be symmetric, to be anti-symmetric, sorry. And then we have to just to compute the coefficients. We have 2 coefficients and we have 2 polynomials. This is the polynomial apply I times dx, so it's a linear polynomial, so you get this relation. The derivative of the linear polynomial is 1, and then you put the third order polynomial. The derivative of that at x equal to 0 is 0, at x equal to 0 in any case is 0, so you get these 2 relations just from computing this, plugging this here. And so you can compute from these 2 relations A and B and you get this. So this is the operator to fourth order. So this is, if you are in any grid, X space grid, so you have a grid here, away from the boundary, say. So you have this point, you use these 4 points. So, and this is generic, right? For doesn't matter what happens near the boundaries or whether it's periodic or not, you use this. This is a good operator when you are reaching the boundary or using periodic, then you have to be careful of what you do. If it is periodic, you just unfold, right, and continue on the other side. So if this is the last point you are going to consider, so this is periodic with this, then you consider the correct points. You consider, if you are here, you consider these 2 points and these 2 points. This one from the left, and this as for the right with this opposite sign. So this is the way you do. So for periodic things it's easy. When the things are not periodic, we have to do some work. So near the boundaries, we will have to change this scheme. We will see that next week. So now we are going to consider the periodic case, because there we can do all the calculations, and it's nice. So these are the matrices we were computing today, but now for the D plus and D minus, D plus and D zero. So you have here, for the first time point, since you are in D plus, you are here, so you take this minus this, and in the last point you take this, which is the next point, minus this. So this is the plus, the minus is similar. And the one we were using today was this one, which is the naught. And notice something important here. This metric is not symmetric. Anti-symmetric, okay? This is not. While this metric is anti-symmetric. So here we know that the eigenvalues are imaginary, but here they have some, in fact we know because we are going to compute them, they have some real parts and some imaginary parts. And this is very bad because we know that the operator dLdx, right? This operator for functions which are periodic, you can, the eigenfunction of these things are e to the I pi x over ln, right? These are the eigenvectors, and these are all, the eigenvalues are all complex, imaginary. The eigenvalues of that is just I 2 pi over ln, this I 2 pi x ln, right? So the eigenvalues are just imaginary. So these ones are not good in that sense, that the eigenvalues are not imaginary. So when we do the Runge-Kutta, for instance, they can have eigenvalues either here or here, say. And in general they cross. So this is pretty bad. They are not good. They are good if you want to treat, I mean, they are good if you, what happens is that, well, let's compute it first, and then we can discuss. It's easy. Another thing that we have to take into account here is that these matrices are what is called sparse. Right? That says that most of the metric is 0. So when we try to compute this, to multiply this by a vector, we used to, it's much better to use some algorithm that knows that these things is mostly zero and only do these calculations, the precise calculations, right? Instead of just doing some multiplication, metric multiplication, which will be almost all the time zero. So we have to either write this specifically for this in a very simple way with a loop, or to use some, in Julia you can use some libraries that tells you that you tell that these matrices are sparse, so they have few places, and so the library just take care and does the computation in an efficient way. So it only puts in memory the ones here, plus ones and minus one and all the zeros, and do an efficient calculation. Because imagine if you are doing, say, if you are taking 1,000 points, then this metric is 1 million, right? Because it's 1,000 by 1,000. So if you just want to put the metrics as it is, it takes a lot of memory. So now we can compute the eigenvalues and eigenvectors of these matrices. As I was saying, the operator, the derivative operator have these eigenvalues where here is a relation that I put before. K over ln is what it goes here. So this is a basis for a interval of length L. It's a Fourier series basis, and so the eigenvalues are this. They are imaginary, and they grow with K. So if you look if you plot these eigenvalues with K, you get a straight line. Now we want to compute the eigenvalues for the finite grid. So we have finite number of points here. And so we can build a base for this grid. Just noticing that this was a base, and now we can take only the elements that are different, because right, these are basically sines and cosines, so they go like this. And if you take some of these elements but at high frequencies, then the grid doesn't see it. For instance, suppose you have a point here and a point, say, here. If you take another of these functions that goes twice here, it will have the same value, right? So these two are equivalent for the grid. So we have to stop the frequencies at some point and not consider all the eigenfunctions, but only a small set. And the condition is this that is here, so that we are going to take these numbers to be like this. So the Kn are finite. So the Kn for this case of the grid are this. So this number is less than 1, and then we have this other number, which is the grid number, the point in the grid. So XL, instead of having XL, here we are mixing the Kn with the XL, right? This, remember, was delta X, times L, and so we are using delta x, that is L over n, to get this relation. Right? So in the exponent, it goes like this. And so the kn's, other way of saying is n over L. And the k's here, they go from minus n over 2 to n over 2. So this is a set of eigenvalues we are going to take. When you are in a grid, you don't do Fourier transform or Fourier series, you do Fourier interpolation. That's the technical name. And Fourier interpolation is given as a vector. You find the wave numbers so that when you put the wave numbers with the eigenvalues, you get the exact values. So it's an interpolation. It's not on L2, but it's an interpolation. So now we are going to use this base and check see what happens when we apply it to the finite difference operator. So here we apply to the D plus or D minus, apply to this one, at the value L, okay? We have this, so X is XL. So is this XL2 plus 1 minus XL. And now you write this as a product of the things of this as XL times the distance to the from XL to XL plus 1, which is this one. Nice. This is because L plus 1 is at the dx here. So the difference between XL and XL plus 1 is dx. So you write this way. So this, you see, the function comes out. So this is automatically an eigenvalue, an eigenvector, and the eigenvalues is this in here. So this is the eigenvalue. It's very straightforward. And this in general is complex because we have here a complex number, minus 1, so this is going to be complex. While if you do the D naught, that is the center derivative, then you have from this side you have this term, and from the other side you have this term with a minus 1 here. So the ones cancel and you get this thing here. And this here is the difference between two terms, exponentials with plus and minus. So it's a sign with an I. So the eigenvalue is this thing here. It's I times sine 2 pi k dx over dx. Notice in the limit dx going to 0, here you have you can write this as I 2 pi kn times sine of 2 pi kn dx divided by 2 pi kn dx, and when this goes to 0, this goes to 1, so in the limit this goes to 2 pi I kn. So in the limit goes to the straight line, this value. So when dx is very small, when you are looking here, it looks like also linear. So here you have an exercise. You can compute the eigenvalues for the fourth order operator that we had, and I have computed here for up to the eighth order, and here you have the eigenvalues. They start at 0. I don't know why I have this. Let me see. Why I have negative here. I don't know why I have it negative. It should be, because, no, it's okay. Here is a 0. So you see, for the first wave numbers, this is very nice. They all coincide. But then, for instance, for the second, you have a departure. For the highest one, you have a departure here. And notice that this is the tangent to it is this is the speed, the propagation speed. So here the speed is constant, is 1. But then when you go to higher wave numbers, there is a point where the speed is 0, and then for your highest wave number, the speed is negative and bigger than, look at here, the speed here has a tangent which is bigger than 1. So these operators produce propagation speed which are bigger than 1 for the high frequency modes. So this is, I have to be careful with that, because for instance, once I was looking at the propagation of waves from a black hole, so I have a black hole here at some, I have a black hole here, so we put some data here and look at the data to go away. And since we are doing a simulation, a numerical calculation, there is a boundary here, far away, and we want to see what remains here. And so you study the solution here, but there is a point, where it is, I lost. Yeah, but no. It will appear, but yeah, but I want to, okay, like this. So we were looking at this is black hole here. We were looking here, and at some point, we were hoping, okay, this is going to go to the boundary, and most of it is going to go out, but there will be something tiny thing that is going to enter because the boundary condition is not perfect. There are numerical errors. So we expected to have something here. So our calculation was going to be valid up to here. But actually we find something else, something previous around here. And this is why there is something which is going faster than light that is coming here. And this is because we were using I think the sixth order operator, and we have this error here. For these modes, high frequency modes, we have a bigger velocity, propagation velocity. So here in the boundary we produce something very high order, just error, and this came very fast. So I remember the velocity was 1.66, I think. and you can compute it from here. So one have to be careful with that. And also that, notice, this mode, there was a mode that was going out, right? And here we have something incoming, because the velocity here is the opposite. So we have a, say, a wave like that. We should be moving this way, but if you put high frequency, actually the approximation in high frequency is going to move in the opposite direction and faster. So one has to be very careful with this. So high frequency behave very differently. That's why we usually cancel this. What we do is to use some operators that cancel all this part. If you have high frequencies, you send them to 0, so you stay always here. And these operators are called Kreis-Oligger operators, and are of this type. So you take the D plus operators, you apply, or D minus, you apply P times, then you apply another P times the D plus, multiplies by X to the pi, to the P, and this is a factor just to make them positive or negative, I don't remember. And so these things acts, this thing gives to the eigenvalues, they give a negative part, negative real part, which is very big for high frequencies, so big derivatives, and is almost 0 for low frequencies. So this takes the high frequencies and cancels them, sends them to 0. So there is a real part which only enters negative real part for the high frequency. And here you can see the eigenvalues of them. I have a plot here. This one. So you see for the Kreis-Oligger operator with only P equal to 2, you cancel all this and all this, because here this is the negative real part. It's with a plus sign, but this is going to contribute to the negative real part. So you cancel all these frequencies, which are too many. But if you use, say, one of these, the K-Oligger order 8, you cancel from here on. Right? Here you don't cancel anything. So if you are looking at smooth solutions which are smooth, then not high frequency, then this is very good, because they don't do anything to this area of the frequency spec of the wave number, but yes, they kill the rest.
There are two questions in the chat that I couldn't see in time.
Okay.
So maybe one question. One of them asked, so the spectrum of a difference operator needs to guide the negative side of the plane, right?
Yeah, or in the imaginary.
In the imaginary plane.
Yeah. So
it needs to be inside the stability region.
yeah. So you want to be, your differential operator has to be in the stability region, right? The eigenvalues. So for instance, if you are in Rugecuta 4, that was a question. If you are in Rugecuta 4, where the stability region is something like that, then you need to be here. So when you use Runge-Kut denote, you are here, but if you use Kreis, you put a Kreis operator here, then you are here. You are around here. For the low frequencies, you are very close to the imaginary axis, and for the high frequencies, you come here. And so when you put the Kreis-Oliger operators, I have problems going back with this. So these are the lambdas, the eigenvalues for the Kreis-Oliger. So they have this form. This is what is not what. This into the 2p, because that's a thing you get one from the plus, you get a plus, and the other you get a minus, so you get the absolute value of them, and this is like this. So they grow a lot with dx, 2 to the p minus 1. But so you multiply them. Let's see if I have the multiplication. No, I didn't. Let's see. So what you do is you, 1 second, let me check this. Yes, there is a mistake here. Here this should be dx to the p times u to the 2p. So this is the 2p derivative. And so the Kreis-Oliger, if you apply it to a function which is twice p differentiable, it gives an error of this sort. When you evaluate, it gives this, x to the p times this. So if the function is nice, this goes to 0 like dx to the p. So the Kreis-Oliger operator goes very fast to 0. It is in. So if you take a derivative, a finite difference, which is order p, the error here will be delta x to the p. So if you add to this the Kreis-Oliger 2p, then this one will also have an error like this. So this is about du dx plus an error, which is order del dx to the p. So it doesn't change the error of the differential operator, the finite difference operator, but kills everything that is higher order. So when you use in conjunction with this, here doesn't do anything, but here it does. It kills all this part. So in general, one puts this operator. But one has to know that one is only interested in this region, right? So if the phenomena has some wavelengths particular, you want to make sure that the wavelengths for this phenomena is in this range, and not here. So you don't care about this. So this is, let's stop now. Then we have to talk about Fourier interpolation a bit. Here we are going to repeat a bit what we did today, but with the eigenvalues. And here we have the phase velocities plots and the group velocity plots. And then I don't know why I have this in here. Okay, I'm going to partition this because I don't know what it does here. It seems I'm mixing up two things. But I'm going to finish this part on Monday, okay? And then we are going to use summation by parts operator when we have boundaries. But this we are going to see later on. Here we have initial boundary value problem. So wait until maybe Wednesday or so. Okay? Any questions? Are there questions there? No, nothing? They are in where you in these notes where I show this. They are you have them available in one of the Git repositories, and there is a notebook where you can get play and do all these plots. So these plots I was showing, they are in the notebook, and they are the derivative operators and everything. So you can, if you want, you can play with it. Okay. Here we go for lunch. So see you on Monday. No, this afternoon, okay. We have consultations this afternoon at today.
Is the repo in GitLab updated or the one in GitHub?
I think it's GitLab. It is. So we meet at 14 hours, huh? For discussions. So here you have to talk. I'm not going to talk. Okay. I don't know how to kill this.
The private GitLab, ¿no?
¿Eh?
El GitLab private.
No, está en el... Pero donde está el private, pero está para todo. Apuntes varios, creo que sí. Ahora hay un montón de mensajes, pues esos mensajes eran viejos.
No, ahí está viendo el que ponga el link.
Ah, el link.
Ahí pongo todo el link.
Ponelo vos. Oh, no sé cómo irme